falling hammer. A hammer with mass m is dropped from rest from a height h above the Earth's surface. So it is dropped from rest, initial velocity 0, at a distance height h from the surface, so at a distance re plus h with respect to the center of the Earth. This height is not necessarily small compared with the radius r sub e of the Earth. Ignoring air resistance, derive an expression for the speed of the hammer when it reaches the Earth's surface. Your expression should involve h, re, and me, the Earth's mass. Now we notice that the system of the hammer and the Earth is isolated in space. There is no energy exchange, there is no friction. Therefore, in this process, we can write the mechanical energy of the system must be conserved. Delta E mechanical is equal to 0. So my task is to write the initial kinetic energy plus the initial potential energy and set it equal to the final kinetic energy plus the final potential energy. The initial kinetic energy is 1 over 2 mv initial squared plus then I have the potential energy which is minus g mass of the Earth divided by re. So mass of the Earth I show with m sub e. Re plus h, and this must be equal to the final potential energy, which is 1/2 m. Final kinetic energy is 1/2 mv final square minus g mass of the Earth divided by re when it hits the Earth's surface. Now, notice that for the kinetic energy of the Earth and final kinetic energy of the Earth, I don't write anything. So I'm assuming that the kinetic energy of the Earth is 0 or it doesn't change. So delta K for Earth is 0. Okay, in this process, delta K for the Earth is 0. All right, and also it was dropped from rest, so the initial kinetic energy of this mass was 0. And I see that the m's cancel here. And I'm left with an equation for V final. V final squared divided by 2 is equal to g times mass of the Earth 1 over radius of the Earth minus 1 over radius of the Earth plus h, the distance from the surface. So this gives me for V final 2g mass of the Earth. Then I have radius of the Earth plus h minus the radius of the Earth divided by re times re plus h square root. And that gives me for V final 2g mass of the Earth times h, because I see that these re's will cancel. And I have re times re plus h at the bottom, and this is all in square root. So that's the final answer. Okay, so we talked about a hammer that is dropped from rest at a height h towards the surface of the Earth, and this altitude is not very small compared to the radius of the Earth, so we have to take it into account. There is no air resistance, no friction, and also the system of the Earth and this hammer is isolated in space, so delta E mechanical is 0. The initial kinetic energy is 1/2 mv initial square, which is 0. Initial kinetic energy of the Earth minus gm mass of the Earth divided by Re plus h. That's the initial potential energy for this configuration. And then I have 1/2 mv final square plus kinetic energy of the Earth, but initial and final kinetic energies of the Earth are the same. So it is delta K is 0. And I have minus gmme over Re. So V final can be solved. We can solve for V final by isolating it, and we find it is square root 2g meh over Re times Re plus h. It is given in terms of h, Re, and me, the Earth's mass as expected.